Okay, ladies, I haven't done this in the last year or two, so we're gonna learn together. I've definitely taught this before, but I wanted to provide a video for those of you who are at home. I know zooming into class, particularly for calculus, is very tough, so hopefully you'll get something out of this. Okay, so we're gonna start at the beginning. We're gonna find x and y-intercepts. The y-intercepts are always the easiest, so catch those points first where you can. Y-intercepts means you're setting the x to 0 and you're finding the y. So here, if I put 0 in for those, the y-intercept is going to be y equals -1. So we know that our graph crosses the axis at y equals -1. I'd also like to rewrite this function as -1/4 x to the 4th plus x squared minus 1. I find that might be easier to visualize for me. Okay, and when I'm looking for x-intercepts, generally I want to factor this whole thing and set equal to 0. Set the y equal to 0, because x-intercepts happen when the y is equal to 0, right? So I'm looking for spots where we can do that. So let me just start that there, and I'm probably going to need another piece of paper at some point. -1/4 x to the 4th plus x squared minus 1. Now this kind of has a weird form, because usually when we're factoring quadratics like x squared and linear x and then that. But let's replace some of this. I'm going to actually change this problem around. This fraction at the front, it makes me kind of uncomfortable. And I love fractions, and I'm imagining that you guys don't feel necessarily the same way. So I'm going to factor out a -1/4. So that means I'm kind of dividing each term by -1/4. Well, if I divide 1 by -1/4, so let's just put that over here, 1 divided by -1/4. Remember that we are in fact multiplying by -4, so it's going to be -4, right? So if I multiply -1/4 times -4, I'll get back +1 squared, which is what we were at originally. And again here I have -1 divided by -1/4, so that's kind of like that. So it'll be a +4. Okay, and that's still the same equation. You'll notice that if I distribute this back out, I have that there. Okay, so let's move forward. This is not going to give us an x-intercept because there's no x value. Like, this won't be 0 ever. So let's just factor this now. Okay, and I need things that multiply to 4 and add up to -4. So I'm going to do -4 and -1. Is that going to add up to -4? Ooh. Well, -4 and +1 won't multiply. 2 and 2. We'll have -2 and -2. That will indeed multiply to +4 and add up to -4. And here I need them to multiply to x to the 4th. So x squared and x squared. Let's check this. X to the 4th minus 2x squared minus 2x squared plus 4. Okay, you're kind of pretending that these are the quadratic and linear terms respectively. You're just going to use a bigger degree up here. So this is a perfect square trinomial. So there are going to be 2 times when this thing equals 0. When x squared minus 2 equals 0, that's a multiplicity 2, then this whole thing will equal 0. So let's just solve for that. X squared equals 2, and then x will equal +√2. So those are our x-intercepts, and just for the sake of being able to graph this, the square root of 2 I believe is about 1.4, so let's just check that on a hunky-dory calculator. So we're gonna go like this, and we're gonna do, let's make it scientific, and do square root of 2. And we got 1.41, so we know it's gonna be +1.41, and square root of 2 is irrational, so we know that goes on for a while. So right now we know our x-intercept, so 1.41 on the pos, okay, -1.41 over here. So those are our x-intercepts, okay? X coordinates are the critical points. So critical points are going to occur where our derivative equals 0. So let's take a derivative of this thing. So we have y equals -1/4 x to the 4th plus x squared minus 1. Our derivative then will be 4 times -1/4. So 4 times 1/4, we said it was 1. It's negative, so -x cubed plus 2x, and that falls out. Well, when is this thing equal to 0? So what we're going to do is we're going to set it to 0. And this is a lot easier to factor. I'm just going to rewrite it. Let's use a clean piece of paper. over here the back of the next sheet just to kind of make that easier. So this is number 1. Okay, and we're setting our derivative equal to 0, so 0 equals negative x cubed plus 2x. Okay, and when is it equal to 0? Let's factor out an x, negative x actually, x squared plus minus 2, sorry. So negative x times x squared is negative x cubed, negative x times negative 2 is positive 2x. Okay, so this is going to be 0 when x equals 0, or when x squared minus 2 equals 0, so x squared equals 2, x equals pos neg root 2. Hey, those are our critical points as well. So we're going to have critical points at x equals 0, x equals positive root 2, x equals negative root 2, and just for the sake of graphing, we're going to write down decimal values, although now that we're in high school we don't really use decimals for much. Okay, so that we've looked at the x coordinates of the critical points, and we want to figure out where it's increasing or decreasing. So here's what we're going to make, just like you did in Mr. Scher's class. You're going to make kind of a table. So I'm going to put these in order, so negative root 2, 0, root 2, and I'm going to check it out and see when is this thing going to become positive or negative. When do we have increasing or decreasing? So here I'm going to have negative x and x squared minus 2. And if I put in values that are more negative than negative root 2, so negative root 2, right? So think of numbers like -3, maybe a number here would be like -1, a number here would be like +1 and +5 or something like that. Let's just use some really easy numbers. Okay, -3 would be positive. If I put in a -3 here, well, it's going to get squared and then subtract 2. So squaring it gives me a nice big positive, like 9 minus 2 is still positive. So here our function is positive, our derivative, sorry, is positive, so we're increasing. Over here between -2 and 0, so numbers like -1, negative 1 is positive, but if I square it and subtract 2, guess what? It's going to be negative. So here my function is decreasing. Do the same thing for +1, that becomes negative. 1 squared minus 2 is still negative. Negative times negative means my function overall is positive, so it's increasing on this interval from 0 to root 2. And then over here, once we're bigger than root 2, this is negative, because negative of a positive is negative. Then I have root 2, or anything bigger than it, squared minus 2. Well, that's positive, so this is overall negative, decreasing. So we get like a nice little idea of what this function is doing. It's increasing, then decreasing, then increasing, then decreasing. So these are indeed, these possible critical points are indeed going to be real critical points. -2, if it goes from increasing to decreasing, must be a max. 0, if it goes from decreasing to increasing, must be a min. And positive root 2 is a max again. Okay, so here we have in our original problem, we now have the critical points. And let's write this down as open intervals so we can see this. So the interval here, the intervals of increasing, are going to be -infinity to negative root 2. Then we're going to be decreasing from negative root 2 to 0. Then increasing again from 0 to root 2. And decreasing again from root 2 to positive infinity. So those are open intervals. We're not including those because at the actual point, remember they gave us 0. Those are actually the critical points. So we've now done this piece of our problem. X coordinates of inflection points. Whenever you see the word inflection, you know that, or concavity, you know that you're looking at second derivative. Okay, we already found our relative mins and maxes, right? We'll have to see if it's absolute later. But let's look at second derivatives. So our first derivative, if you remember from the previous page, was -x cubed plus 2x. So let's write down our second derivative. Y prime was -x cubed plus 2x. Therefore, y double prime is going to be -3x squared plus 2. So 0 equals, again, this is all for points of inflection. We're going to look at 0 equals -3x squared plus 2. And we want to figure out when this thing equals 0. So I'm just going to do this kind of an old-fashioned way. We're going to subtract the 2 from both sides. So -2 equals -3x squared. Divide both sides by -3. there we are. So negative divided by negative is positive. We have x squared equals 2/3, and square root both sides. X equals positive root 2/3. Okay, not a pretty number, but it's a number, and maybe we want to have an idea of what that looks like on a calculator. So I'm just gonna bring that back out. So let's clear off the previous root. The square root of 2/3 is like 0.82-ish, okay? So just taking that back. So posneg 0.816, etc. Again, it's irrational because we can't take the actual square root, so it's going to go on forever and not repeat. But at least for the sake of graphing it, we can do that. So I'm going to use posneg 0.82. Okay. Well, we have to test those points again. So our entire thing is, I didn't factor this out or anything, so we kind of need to we can use the table of values again. So negative root 2/3 and positive root 2/3. And in between them I've got 0, right? This is like negative 0.82 and positive 0.82, so I know 0 is right between them if I had number line. And let's look at what happens to our negative 3x squared plus 2. Okay, well if I go more negative to the left of this, like negative 1, negative 1 squared is positive 1. Negative 3 times positive 1 is negative 3, plus 2 is a negative. So I'm definitely concave down out here at the negative 1s. Okay? If I go between negative root 2/3 and positive root 2/3, numbers like 0. So 0 squared is still 0, negative 3 times 0 is 0, plus 2, I got positive, so this is concave up. And let's go to the right of positive root 2/3, so the whole thing's under a root. Okay, so if I put in positive 1, I have negative 3 times positive 1, so that's negative, plus 2 is still negative, so we're concave down over here. So indeed, these are points of inflection, POI, or inflection points. So I know that those 2 points, when x equals those 2 points, I'm going to have a change in concavity. Okay, so let's go back to our original question, see what we have. We have the x coordinates of the inflection points, yay. We have the open intervals where the function is concave up and concave down. So let's write this interval notation now. Well, if I go from negative infinity all the way to negative root 2/3, we're going to be concave down. If I go from negative root 2/3 to positive root 2/3, I'm going to be concave up. And I'm going to be concave down from positive 2/3 all the way to infinity. So now I've done my intervals, okay, of concave up and concave down. And we did relative min and max. We found our x coordinates, but we never found our y coordinates. So that's the last piece here. So if we put in f of negative root 2, f of 0, and f of positive root 2, those should give us the y coordinates of our max and mins. So this one we said was a max from here, and my function originally was this kind of wonky thing. My original function, f of x, was negative 1/4 x to the 4th plus x squared minus 1. So negative 1/4 of negative root 2 to the 4th power plus root 2 squared minus 1. So it's nice that the roots here are getting to an even power, because that will make our life a lot easier. So we have negative 1/4. Okay, now I'm going to ignore the negative sign, because a negative sign to the 4th power is just going to be positive. So root 2 squared will just be 2, and then square that again will just be 4. So negative 1/4 of 4. Then we have negative root 2 squared, that's just going to be 2, so plus 2 minus 1. So negative 1/4 of 4 is just negative 1 plus 2 minus 1. Hey, that's going to be 0. Nice. So one of our points, our maximum that we described down here, is actually negative root 2 comma 0. That's our point. We're going to do this again for 0. When I plug in 0, I'm going to get negative 1. That's our y-intercept. So the point here is 0, negative 1. That's kind of a min. That's our point, and it's one of our mins. And then when I plug in positive root 2, it's going to be the same thing. Notice this is an even function. If I plug in a positive or a negative, it's going to be the same thing. So I don't do all that work again. I'm going to get 0 again. So I'm going to get root 2 comma 0. And that's another point. That's another one of my critical points. And we can decide which of these are maxes or mins. Well, these two, we know that our function is a negative quartic function, right? It has this degree 4, and it's negative, so it's going to face downwards. So something like that. That's from algebra 2. So we know that these 2 points actually have the same y-coordinates. So there's no absolute, these are both absolute maxes. Here's my relative min, and because it continues on downwards, there's no absolute min. So let's graph this this chunky thing. We already graphed x-intercepts. We already graphed our y-intercept. Now we need to go to our negative root 2. We know this is our max. Let's put in our concavity. Well, we know it goes something like this. We're going to connect it with a curved line. Okay. And we know that this part, till we get to negative 0.82, so somewhere around there, we're going to be concave down. So this part is concave down, and this part should be concave up. And then again on this side, concave down. And the whole thing continues to be concave down, and here it continues. So notice that here we have an inflection point, right? That's what we found by the second derivative. So second derivative points of inflection are both these numbers, and we found that those were x equals positive negative root 2/3, which we said is pos neg 0.82 approximately. Okay, and there's our curve sketch with all of the information. And we've got our local min, our absolute max, and those we don't have an absolute min here.